Hey everyone, it's Suraj, and today we're going to be walking through discussion 7 of the spring 2019 iteration of Data 100. And so in this discussion, we will be talking about the geometry of least squares and thinking about how we can arrive to the solution to the least squares problem. And we will also talk about gradients and work through some common gradients that you'll need to know for this class. Okay, so in the first problem, we're given this diagram that sort of details all of the key players when it comes to the solution to linear regression, but I sort of wanted to walk through this because I think understanding this diagram will go a long way in understanding why linear regression works. Okay, so this plane here, it's sort of already labeled, but it's actually what's called the column space of phi. Okay, and phi is your feature matrix or your design matrix, and for now, let's say phi has n rows and p columns. Okay, so what this means really is that it has p features and n observations, n data points. Okay, and just for now, let's assume that these columns are labeled phi 1, phi 2, so on and so forth, until phi p. What the column space of phi really means is it's the set of all possible vectors we can reach when we multiply phi by a vector. Okay, so it's the set of all vectors phi times v, where v is just a vector. Okay, in this case, a real vector with p elements. Okay, and so that's what this plane represents. And what our job is we want to find the vector theta hat that minimizes the norm of the error. Okay, and what's the error in this case? Well, we'll define the error as being this. The difference between y, which is our true observation, which is not in the column space of phi, right? Just some vector, it's the true results that we have, y minus phi times theta hat, right? Theta least squares is just theta hat. Okay, we want to find the vector theta hat that minimizes the norm of this error. Okay, and so again, the column space of phi is just a set of all possible vectors we can reach by taking the operation phi times v, and we want to find the v, or which we'll call it theta hat, that minimizes the norm of this error. Okay, and so notice if we choose the theta hat, a theta that's not the optimal one, right? So if we multiply by some arbitrary vector v that's not the optimal theta, we can have phi v or phi theta look something like this. Okay, as an example, it really could look like anything. Okay, and in this case, what the error vector y minus phi theta would look like might look something like this. Okay, and I'll just call this error 2 for now. Okay, and clearly this is not the smallest possible error because the one that's depicted in the diagram is clearly smaller. Okay, and what the whole point of this diagram is to show you that the way to minimize the size of the error is to make the error orthogonal to the column space of phi. Okay, and so the key takeaway is that the error needs to be orthogonal to the column space of phi. Okay, and now recall the way we show, or the way we know that two vectors are orthogonal is if their dot product is equal to 0, right? And remember, phi consists of these p vectors, phi 1, phi 2 through phi p, right? And so what we're saying is that the error vector y minus phi theta hat has to be perpendicular to phi 1, it has to be perpendicular to phi 2, phi 3, so on and so forth, through phi p. So what we're really saying is that the dot product of phi 1 and the error needs to be 0, but another way we can write that is phi 1 transpose the error is 0, right? And just as an aside, A transpose B and B transpose A, both equal to the standard dot product that we've seen before if A and B are both vectors. We also need that the second column in phi is orthogonal to the error, and through the pth column is orthogonal to the error. Putting all that together, we can really just say that phi itself has to be orthogonal to the error. Okay, and so the main takeaway from this diagram is that in order to minimize the norm of the error, we need that phi has to be orthogonal to the error. Okay, and that's really what we've arrived at. So phi transpose the error must be equal to 0, showing that the error is orthogonal to the column space of phi. Okay, and I'll expand this out a little bit because we know the error is y minus phi theta. This is really just saying phi transpose y minus phi theta should be equal to 0. Okay, and that's the result of interpreting this diagram. And so that's our claim, and what we want to do now is prove this using a calculus-based argument invoking gradients. Okay, and so recall the function, and I can say it's a function of theta, we're looking to optimize is the error, right? So we want to optimize the norm of the error. We want that to be as small as possible, but what's the error? That's just y minus phi times theta squared, the L2 norm of it squared. Okay, and just for the purposes of this question, I'll let x be equal to phi. Why is that? Just for clarity. Because, sometimes if you're writing fast, the phi's and the thetas might look a little similar, and so I'll just use x. But in general, x usually represents a raw set of points, whereas phi is a feature matrix where you've done some transformations to your raw points. We will use phi basically in all instances in this course, but just for this derivation, I want to use x just because it looks a lot more different than theta. Okay, so we're looking at the L2 norm squared of y minus x theta in this case. Okay, so don't forget this. Our x really should be phi. Okay, so before proceeding, we need a couple facts and gradients of revolving around matrices. Okay, so the first, which we've sort of already seen, is that the L2 norm squared of a vector is equal to that vector transpose itself. Okay, which is also equal to the standard dot product that you're used to seeing. Great. The next one, which we'll actually derive in question 3 of this discussion, so you can skip ahead a little if you want and then come back to this question, is the gradient with respect to x of X transpose A, which is the same as the gradient with respect to x of A transpose X, is just equal to A. Okay, and this is a fact that we prove, again, in the second last question of this discussion. The last one we need is that the gradient with respect to x of X transpose AX is A plus A transpose X. Okay, we don't walk through the derivation of this, it's a little more messy, but you sort of have to know it. Also, in the case when, oops, that's a little weird, but in the case where A is symmetric, this happens to be equal to 2AX. Okay, because when A is symmetric, A and A transpose are the same matrix. Okay, and so what we'll do now, before taking a gradient with respect to theta, which is what you need to do when you want to optimize a function in terms of theta, we will rewrite this the norm squared of the error in a way such that we can use each of these properties, right? Because these are really the only gradients we're expected to know at this point. Okay, so the first rule I will use is the fact that the norm squared of A is equal to A transpose A. So I can write this here as y minus x theta transpose y minus x theta. Okay, and let me expand that out a little. I can write that as, just to show an intermediate step, y transpose minus theta transpose x transpose y minus x theta. And there we just use the fact that AB transpose is B transpose A transpose. Now we can just, do your standard binomial multiplication. We have y transpose y, minus y transpose x theta, minus theta transpose x transpose y, minus theta transpose x theta. Okay, and remember we're going to end up wanting to take the gradient of this, and we see that this very last term looks a little similar to this, right? Because we're going to take the gradient with respect to theta. So theta over here is really x over here, and we have theta transpose blank times theta, and so that we're fine with the last term. And we know that this first term is independent of theta, so when we take the gradient with respect to theta, it will drop out, right? Because it has no affiliation with theta, it will be 0. Okay, and so the last sort of simplifying step we need to make is with these middle terms. Okay, and so the claim I will make to you is that both this first term and second term are actually equal. Okay, and so let's look at that. It turns out they're both actually the same dot product. Okay, one is y transpose x theta, and the other is x theta transpose y. Okay, it's just expanded out in the other way as being theta transpose x transpose. But as we discussed over here, those are both equal to the dot product of y and x theta, which is just some scalar. Okay, they're both equal to a scalar, and so they have to be the same scalar. And so what I'll do, in order to write this in terms of theta transpose times something, so that I can use this gradient rule over here, I will write this as minus 2 times theta transpose x transpose y. Oops. Okay, there's several ways I could have written this expression. I could have written as y transpose x theta if I wanted to, but then recall we're about to take the gradient with respect to theta, and I want to be able to use these gradient rules that I have over here. Okay, and in order to use this second rule, I need to have it in terms of theta transpose something. And this is the only way to write this expression as theta transpose something, right? Because that's what we know to take the gradient of. Great. So now we're at a stage where we can take the gradient. So let me take the gradient of f with respect to theta. And now the first term, as we mentioned before, that drops out because it's independent of theta. Now the second term, I have 2 times, now the gradient of theta transpose something with respect to theta, that's just something. Okay, and again, we're invoking this rule over here. The gradient with respect to x of x transpose A is just A. And now we want the gradient of theta transpose X theta with respect to theta. Okay, and we notice X transpose X is symmetric. Okay, so in the case where A is symmetric, the gradient of X transpose AX is just 2AX. Okay, so in our case, we don't have A, we have X transpose X, and the X over here is replaced with theta. So the gradient of this last term with respect to theta is really minus 2 X transpose X theta. Okay, and what we're going to do is set this equal to 0. Okay, so what we've done is we have dividing both sides by -2. I have, do the signs match up? Oops, yeah, sorry, my mistake over here. This should have been a plus, this should have been a plus, and this should have been a plus. Sorry about that. Now, if you look at what we have, dividing both sides by 2, I have X transpose X theta minus X transpose Y is equal to 0. Okay? And what do we have over here? Well, this is really saying X transpose X theta minus Y is equal to 0. And since it's equal to 0, I could just multiply this whole thing by -1 and rewrite this as Y minus X theta. Okay? Which is exactly what we wanted to show, right? Again, with just the x's, they should be replaced with phi's. What we showed down here is exactly what we claimed above, right? And how we did that was we started off with our function being the L2 norm squared of y minus phi theta. We took the gradient with respect to theta, set it equal to 0, and found this relationship has to hold true. We haven't found the actual optimal value of theta. We're about to do that in the next part. But we've shown that the relationship that we claimed to be true actually holds true. Okay, and so now we can just continue from the last part. We have this relationship X transpose y minus x theta is equal to 0. I can expand this back out to the step I had over here. X transpose y is equal to X transpose X theta. And what I can now do is left multiply both sides by the inverse of X transpose X theta. Okay, so I can move, get some room over here and say this is X transpose X inverse, and then X transpose X inverse over here. Cancel out over here, and we're left with theta hat, right? Because this is the optimal value, because it's the value I've gotten by taking the gradient and setting it equal to 0. Theta hat is equal to whatever we have over here, which is X transpose X inverse X transpose Y. Okay, and now remember, we actually had that X is equal to phi, and to write everything in terms of phi, I can just have phi transpose phi inverse phi transpose Y. So we've concluded the proof. Okay, so before we proceed, because question C is a little, I wouldn't say unrelated, but it's independent of parts A and B, I just wanted to walk through what we just did. So we started off with this geometric interpretation of what the column space of phi is, what y is, and what this error vector is, and we determined in order to minimize the norm of the error vector has to be orthogonal to the column space of phi. So we have this relationship phi transpose y minus phi theta should be equal to 0. And then with that in mind, we started fresh and said, okay, well, really what we want to do is minimize the norm of y minus phi theta, right? The L2 norm of that squared. We use some convenient vector properties and gradient properties to take the gradient of this function with respect to theta, set it equal to 0, and we found the optimal value of theta. Okay, and that optimal value of theta is phi transpose phi inverse phi transpose y. Okay, one little nuance that I didn't mention yet is, well, how do we know that this is a minimum and not a maximum? Well, it's because the L2 norm function is convex. Okay, and that's something that is probably discussed in lecture. Okay, but just something to keep in mind. Okay, so that's what we've done so far in parts A and B. Now moving on to part C, we again have phi being defined the same way, has n rows, p columns, and it has full column rank, which means that the rank is equal to p, which is the number of columns. And we're going to be investigating this new matrix H. Okay, phi times phi transpose phi inverse times phi transpose. Okay, that appears in linear regression. Okay, and in the first part, we're told that a projection matrix is a matrix that when you square it, it gives you back the same matrix. And so what we want to do is show that H is a projection matrix. So what we want to show, RTP means required to prove, we want to show that H squared is equal to H. Well, what is H squared? It's just H times H. And well, what is H? It's phi times phi transpose phi inverse phi transpose. Okay, so to multiply this whole thing by H, I can copy it, paste it again. And now we can use the fact that multiplication is commutative, meaning I can do it in any order to simplify things. Okay, so I can arbitrarily place parentheses around what we have here. And notice I have phi transpose phi inverse times phi transpose phi. Right, and the matrix times its inverse, by definition, gets us back to the identity matrix. Okay, so this really is phi times the identity times phi transpose phi inverse phi transpose. But the identity doesn't change the value of this multiplication. That just brings us back to phi transpose phi inverse phi transpose, which by definition was H. So we've shown that if we take H and square it, it brings us back to H, meaning it's a projection matrix. Now in the second part, we want to show that if we multiply H by Y, we get Y hat. Okay, so an important thing to keep in mind is what exactly is Y hat? Well, Y hat is just phi times the optimal value of theta, which, remember, from up here, the optimal value of theta is phi transpose phi inverse phi transpose Y. Okay, so what we really want to show is that HY is equal to Y hat. Well, with this definition in mind, that comes out pretty easily, because HY by definition, H is just phi transpose phi's inverse, phi transpose, and now I tack on a y there, and well, the right-hand side of this expression is exactly this expression over here. So I can claim that this is y hat, and we're good. Cool. In part 3, we want to show that M, which is I minus H, is also a projection matrix. Okay? Well, again, what we're required to show is that M squared brings you back to M. Let's do that. So M squared is just I minus H times I minus H. And we can distribute our multiplication the same way we do with scalars. So I have I squared minus I times H minus H times I plus H squared. Okay, now we can simplify many of these terms. Okay, I squared is just I, right? When you square the identity, you get back to the same thing. I times H is just H, right? Because when you multiply a matrix by the identity, it doesn't change. And then again, H times I is also H. And then H squared, we showed up here, is just H, right? We showed up here, H squared brings back to H. So we have plus H over here. The last two terms cancel, and now I'm left with just I minus H, which was what we defined M to be. So we've also showed that M is a projection matrix, because when you square it, it brings it back to M itself. Now lastly, we want to show that My results in the residuals of the linear model. And so the residuals are really just the error, right? So we're going to show that My ends up being equal to E, which is Y minus Y hat, which again is Y minus this quantity over here, phi transpose phi inverse, phi transpose Y. Okay, and as we've come to expect, this term over here is H, so we really want to show that the error is equal to Y minus HY. Okay, so let's look at My. We know M is just I minus H times Y, and this gives us IY minus HY. And remember, multiplying a vector or a matrix by the identity doesn't change it, so we have Y minus HY, which is what we have over here, which is what the errors or the residuals themselves are. Okay, so we've shown that when you multiply matrix M, which is just I minus H by Y, it gives you the residuals or the errors. Okay, now in part 5 of this question, we're told, notice that the hat matrix is a function of our observations phi rather than a response variable. What do the values in our hat matrix represent? Okay, and so for this one, I want to invoke the relationship we saw in part 2 of this question, which tells us that Y hat is really just H times Y. Okay, so we have Y hat is H times Y. And what I want to do is look at the specific dimensions of this vector multiplication. Okay, so Y hat will have, Y hat 1, Y hat 2, all the way through Y hat n is equal to, and so you can actually do the dimensional analysis, but you'll see that H is a square n by n matrix. Okay, we won't do that right now, but that's something you can show. Y1, Y2 through Yn. Okay, and so H will have, something like, H11, H12, dot, 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 through H1n, H21 through H2n, and the last row will have Hn1 through Hnn. Okay, and so what the question is hinting to us is we can write Y hat I as a summation, right? And so, for example, to calculate Y hat 1, we would take the dot product of the first row of H and this column vector Y, right? We would have H11 Y1 plus H12 Y2, and so on and so forth. I can actually write that out here. Y hat 1 would be H11 Y1 plus H12 Y2 plus dot, dot, dot through H1n Yn. Okay, so in general, I just replace the ones with i's. So this would be the sum, where j goes from 1 through n, of Hij Yj. Okay, J counts, from the first column to the second column to the last column, and it also counts these. Oops. Okay, and so what was the point of doing this? What do the values in our hat matrix represent? And so what we really care about is the relationship between observed value I and predicted value I. Right? We care about the relationship between y1 and y hat 1. Relationship between y23, for example, and y hat 23. Right? We don't so much care about the relationship between y2 and the predicted y5, like y hat 5. Right? We really care about yi versus y hat I. And so in each of these summations, one of those terms is more significant than the others, and it's the terms on the diagonal, right? And we can observe that when I look at the summation for y hat 1, right? The thing that we're multiplying y1 by in the summation is h11, right? Similarly, if I were to write out this expression for y hat 2, I'd have h21y1 plus h22y2, right? So the thing I'm multiplying y2 by in this summation is h22, right? And again, we care about the relationship between yi and y hat I, and not so much about the relationships between other actual and predicted. Okay, and so the diagonal elements sort of represent the weightings of each of our observations. Okay, and so the actual term, and you can sort of read more about this in the solutions document for these diagonal elements, are called leverages. Okay, and the larger leverages, so the larger HII is for a specific I, the more influence that the point YI has on the prediction Y hat I. Okay, and finally, to wrap things up for question 1, part D, it tells us that we can show that phi and phi transpose phi have the same rank, and we want to list some reasons why phi might not have full column rank, which would imply that phi is not invertible, meaning phi transpose phi is also not invertible. Okay, and just recall, we have phi as n rows, which means n observations, / data points, and we have p columns, i.e. features. Okay, and in a linear algebra class, you might have learned that the rank of a matrix is the same as the dimension or the number of vectors in its column space, which is also the same as the number of vectors of its row space. Okay, and so the case we want to look at is when there are fewer rows than columns, i.e. the matrix is fat. Okay, and I'll write out one example of this here where we only have 2 rows but many columns. Okay, so for example, suppose we have x11, x12, ... x1p, and for example, x21, x22, x2p. Okay, in this case, clearly we have fewer rows than columns, and the dimension of the row space either is 1 or 2, right? It's impossible for the dimension of our row space, i.e. the number of linearly independent rows, to be greater than 2 because there's only 2 rows, okay? And since the number of rows is less than the number of columns, it's impossible for the matrix to have full column rank, right? Because for it to have full column rank, the rank of the matrix would just be p. But since n is less than p and an upper bound for the rank is n, it's impossible for the rank to be p. So when our matrix is fat, i.e. we have fewer observations than features, then phi will not have full column rank. Another case in which a matrix, our feature matrix phi, would not be invertible is if some columns were linear combinations of one another, right? Which would imply that not all column vectors are linearly independent, right? And you can come up pretty easily with examples of features that you could have that are linear combinations of one another. So, for example, if you had gross expenses, so gross profit for a business expenses and net profit as different features, well, since gross profit minus expenses is equal to profit, that's a linear combination, right? And if those were all different features, your matrix would not possibly have a full column rank because some of your vectors are not linearly independent of one another. Okay, and so just to write that explicitly, when some features are linear combinations of one another. Okay, I think I might have said gross profit as opposed to gross income, but whatever, that's not the point, right? The whole point is if some features are linear combinations of one another, then phi will not have full column rank. Okay, so I think that wraps up question 1. So now let's move on to the gradient part of the discussion, so questions 2 and 3. So in question 2, we're given this 3D plot of this function x minus 1 quantity squared plus y minus 3 quantity squared. If you've taken 53, you might recognize this as being the equation of a paraboloid, but that's not really important. And on the right, we have a plot of its gradient field, okay, and we see that the lengths of the arrows show the relative magnitudes of each gradient vector. Okay, so you can see these vectors that are further away from this point over here, which we'll talk about in just a second, they're longer, which means the function is changing faster further away from this point 1, 3. Okay, so the longer the gradient vector is, the more quickly the function is changing at those points. Great. Okay, so firstly, part A, we're asked, is this function convex? And we can just make a visual argument. Okay, and so when we first learned about convexity, we saw that there were a bunch of equivalent definitions, but a really nice visual one was that for a function to be convex, it must satisfy the property that if we take any 2 points on the function and draw the secant line, right, which is just taking 2 points on the function and connecting them, that secant line always has to lie above the function. Okay, and so in this example, I drew just a shifted version of y is equal to x squared, which of course is convex because I drew the secant line and it's above the points, and I can do that for any 2 points on this function. Okay, the same principle applies in 3 dimensions as well. Okay, if I look at the plot of this equation, I can connect any 2 points on the surface, and it's sort of hard to see this in a 2-dimensional projection, but I'd be able to connect any 2 points on the surface, and it would still lie above the surface. Okay, and so it satisfies the same property of convexity as we've seen before, and so yes, it is indeed convex. If you wanted a more rigorous proof that this function is convex, you'd have to find what is called the Hessian, which is a matrix of second derivatives. Okay, and there's 4 second derivatives, second partial derivatives really of this function we can find, right? Like the second partial derivative with respect to x, the second partial derivative with respect to y, and then the derivative with respect to x then y, and then y then x. And you have to show that that matrix is positive semi-definite to prove that this is convex. But we don't really need to do all that in this question. Okay. Now in part B, we're asked to superimpose a contour plot of this function for f of xy is equal to 0, 1, 2, 3, 4, and 5. Okay, so looking at this equation, we have x minus 1 squared plus y minus 3 squared is equal to k. Okay, where k will take on these values 0 through 5. And this may look familiar. Well, it's because it's the equation of a circle centered at the point 1, 3, which is what we had before, with radius, so a circle centered at 1, 3, with radius square root of k. Okay, not k itself, but it's the square root of k, because in the general form of the equation of a circle, as you may have seen before, is x minus h squared plus y minus k squared is equal to r squared, right? Because it's a set of all points that are a fixed distance r away from the center h comma k. Okay, so what we have is all the contour plots will be circles with the square roots of these numbers here as being the radius. Okay, so the contour plot when f of xy is equal to 0 is really just the point that we have over here. right? Because it's the set of points that are 0 distance away from 1, 3. And then the contour plot when we have k being 1 is a circle with radius 1. Okay. The contour plot when we have k is equal to 2 is a circle with radius square root 2, which will be a little hard to draw. Square root of 2 is about 1.4, so it'll be somewhere in between 1 and 2. Okay, something like that approximately. I could do the same thing for square root of 3, and it would be, again, a little closer to 2, but I'm not that great of a drawer, so we can skip that. We look at k is equal to 4. That's a circle with radius 2, so that will look something like this maybe. And then 5 would be a circle with radius square root 5. Okay, and that's what the contour plots would look like. Okay, and I recommend you look at the solutions document for a little more neat drawing of this question, but hopefully the idea has come across. Okay, part C, what do you notice about the relationship between the level curves and the gradient vectors? Well, one, as I mentioned before, the further you get from this point, 1, 3, the longer the gradient vectors get, right? You notice closer to 1, 3, the gradient vectors are relatively short, and then you get further away, they become relatively long. Okay, so as the radii of the level curves increase, the magnitude of the gradient vectors increase. Okay, so as the radius of the level curve increases, the magnitudes of gradient vectors increase. Great. Okay. Another thing you might notice is that at each contour level, the gradient vectors are actually perpendicular to the contour curve. Okay, and that's because it shows the direction in which the function is increasing, right? Because the contours will just become larger and larger circles, and the gradient vectors just say, okay, we're working outwards. We're going from a smaller circle outwards to a bigger circle, outwards to an even bigger circle. Okay, so it makes sense that the gradient vectors are perpendicular to the contour curves. Part D, from the visualization, what do you think is the minimal value of this function and where does it occur? Well, so looking at the plot that we have on the left, it should be pretty clear that there's only a single minimum value of this function. Okay, it's not like it decreases towards infinity, sort of like a plot that looks like this, right? This function that I just drew down here, sure, it has a local minimum, but it also has no global minimum, right? Because it increases downwards forever and ever. What we'll notice about our function f here, though, is that it has a single local minimum, which happens to be the global minimum, right? Because the function opens up. Okay, and the minimum value of this function is probably where the gradient is equal to 0, where the function doesn't change, right? In a single variable calculus course, what you learned is to find the minimum value of a function, you take its derivative and set it equal to 0, right? You want to find the point at which the function is not changing anymore. And if it's convex, that optimal value you know is a minimum. Whereas if it's concave, you know it's a maximum, right? So our guess is that the minimum value of the function is right here at 1, 3. Okay, another way to arrive at that is, well, let's look at our expression, right? X minus 1 squared plus y minus 3 squared. This really looks like box squared plus triangle squared. And we know box squared is greater than or equal to 0, and triangle squared is greater than or equal to 0. This means that the minimum value that we can have is 0 itself, which we get when both box and triangle are equal to 0. In our case, we would get that by setting x equal to 1 and y equal to 3, which is where the gradient of the function is actually equal to 0. So whichever way we want to approach it, we'll find that the minimum value of this function is at the point 1, 3. Okay, to do this a little more formally, why don't we calculate the gradient of the function, right? And so the gradient of the function will be a vector of all the partial derivatives. So the partial with respect to x and the partial with respect to y. Okay, and just as a reminder, what's our function? Well, it's x minus 1 quantity squared plus y minus 3 quantity squared. So what's the derivative of that thing. Let's see, f is equal to almost 1 squared plus y minus 3 squared. What's the derivative of that with respect to x? Well, it's just 2 times x minus 1. And what's the partial derivative of this with respect to y? Well, that's 2y minus 3. Okay, so that's the gradient. And now when the gradient is equal to 0, meaning all the elements are set to 0, what are the values of x and y? Well, that would require 2 times x minus 1 to be 0, which of course occurs only when x is 1. It would also require 2 times y minus 3 to be 0, which only occurs when y is equal to 3. And again, that sort of indicates to you, since the function is convex, the minimum value is when the gradient is 0, which is at 1, 3 in this case. Okay, so this question sort of walks through the relationships between contour, plots, gradient vectors, and gradients of a function. Okay, and so the main idea is that you want to take the gradient, set it equal to 0, and solve to find the minimum value of a function, which you can do when the function is convex. Great. Now moving on to question 3, where we will work through some of the mechanics of actually finding gradients of various functions. And we're sort of given some notation. Little x is a scalar, bold little x is a vector, big X is a random variable, and bold big X is either a matrix or a random vector, and don't really have to deal with that for this question, but as it says, context will tell. Okay, so first we want to find the derivative of a0 plus a1x, okay? And that we can do pretty easily. It's just a1, right? Because a0 is a constant, and we can get that pretty easily from the power rule. Now we want the gradient of g, right, which again is a vector of all possible partial derivatives. Okay, so it's the partial derivative of g with respect to x1 and the partial derivative of g with respect to x2. Also note, sometimes just because we don't have a lot of vertical space on these pages, oftentimes we'll write it in the transposed form, right? So like this, but it's really the same thing. And now, what's the partial derivative of this function with respect to x1? Well, this term and this term are irrelevant because they have no x1, so it's just a1. And similarly, what's the partial derivative with respect to x2? The first and second terms are irrelevant because they're independent of x2, so we just get a2. Okay, so the gradient, of g is a1, a2, the vector of that. Okay, and so the point of this question is to lead us into part B, which is suppose that x is an n element vector with x1, x2 through xn, and our function h is the result of taking the transpose of A and multiplying it by x. Okay, this is really just the dot product of A and x. Okay, and we could have written it the opposite way as well. We could have said xta. Either way, and sorry, we're told that A is a similar vector, which is a1, a2, dot, 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 through an. Okay, we're taking the dot product of these two things. When we take A transpose X or X transpose A, we'll end up getting this expression, a1 x1 plus a2 x2 plus dot, 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 plus an xn. So you can see that this is essentially a continuation of the previous part, right? We have a1 x1 plus a2 x2. Now we're just adding on a3 x3, a4 x4, so on and so forth, through an xn. Great. So now we want to find the gradient, right? Which means we want the partial of h with respect to x1, partial of h with respect to x2, so on and so forth, right? Of course, it's transposed. Okay. What's the partial of h with respect to x1? Well, that's just a1, right? With respect to x2, that's just a2, and so on and so forth, until we get an, transpose. But this vector over here, this vector over here is the exact same as this vector over here. So it turns out that the gradient of h is just a. Okay, and you can think of this as being the vector version of this specific case of the power rule, right? The derivative, if f of x is ax, the derivative is a. Okay, it's not the exact same, but you can sort of see the parallels there in a very abstract sense. Okay, so hopefully it's clear that the gradient of A transpose X, or equivalently the gradient of X transpose A, both equal to A. Okay, and now part C, we want to look at the gradient of X transpose X. Okay, remember I stated before, A transpose X is just the dot product of A and X. So X transpose X is just the dot product of X and X. Okay, and so f of X in our case, being the dot product of X and X, really just looks like x1 times x1 plus x2 times x2 plus dot 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 plus xn dot xn. Okay, which is really x1 squared plus x2 squared plus dot 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 plus xn squared, right? Now to take the gradient, we again want a vector of all the partial derivatives. So the partial with respect to x1, partial with respect to x2, so on and so forth, until we have the partial with respect to xn. And now it's the partial derivative of this function with respect to x1. Well, the terms x2 through xn are irrelevant, so now we're just looking at the derivative of x1 squared with respect to x1. Well, that's just 2x1. Okay, similarly, what's the partial derivative of f with respect to x2? That's 2x2, right? Just by using the power rule, and all of the other terms are irrelevant. And so on and so forth until we get 2xn. Okay? Right, and just again to reiterate, when we're looking at the partial derivative with respect to x1, the only term that really contributes to the derivative is the first one, right? Because the other terms do not contribute because they're independent of x1. Okay, and so what we notice is there should be a transpose over here and a transpose over here. Great, because by convention we have column vectors. And what we notice is that this is really just 2 times the vector with x1, x2 through xn transpose. And this vector over here is just x, right? Because we're told by definition up here, that's what x is. The column vector with x1 through xn, we wrote it as a row vector, so we have the transpose. So the gradient of f is really 2x. Okay, and the scalar parallel to that is that suppose you have the scalar function f of x is x squared, which is sort of what this is, x multiplied by itself. The derivative of that is 2x. Okay, and it's not exactly the same, but you can see the parallels. Okay, and in fact, what you could do is suppose x was a one element vector, right? So really just a scalar. You can show that this formula holds, right? And sorry, not that it holds. Of course it holds. It holds for any n, right? But you can see that it's the exact same as the scalar version of the formula, right? Because one element vectors are really just scalars. Okay, so we've shown that the gradient of f in this case, so the gradient of x transpose x is 2x. We did the same for part B and part A. Okay, so that wraps up the gradient section of the discussion, and that actually wraps up the entire worksheet. Okay, and feel free to post on Piazza if you have any clarifying questions.